This is the Enigma machine. It's a cipher device where you can type a message and get it encrypted. Enigma was invented in the early 20th century and used extensively by Nazi Germany during World War II. It's funny because I started looking for something different before I realized that I was in a rabbit hole about encryption and ancient books about ciphering text and replacing information with secret codes. But here is what I want to share with you and what led me to all of this. While Enigma and all of these ciphering mechanisms obfuscate information, make it hard to interpret, we often use similar principles with a very different purpose. As soon as you start looking into different algorithms and techniques to build models that learn from data, you realize that many, if not most of them, don't like text. They can process it directly. They only work with numbers. So before we can use any of these algorithms, we must encode all text in a way that computers understand. That's the only way to make them work. This process is called encoding, and in machine learning, there are many different ways to do it. But there's one specific encoding technique that I find really interesting, and I only learned about it a couple years ago as part of a machine learning competition. So let me show you the simplest encoding technique you've never heard of. So here I have some weather data I tracked over a few days. This is the conditions on that day, whether it was sunny, cloudy, or rainy. The temperature that I tracked in Fahrenheit because, well, that's the way you do it where I live. And then I tracked my mood during those days. Very simple. It's either happy or sad. Now, of course, there is a lot of text in this data. I have the condition category with 3 possible values and the mood category with 2 possible values. And all of that is text. If I wanted to use this data with a machine learning algorithm that doesn't work with text, I would need to encode all of this. I will need to use numbers instead. Now, there are 2 popular techniques that most people use when doing this. The simplest one of those is to assign a consecutive number to every possible category of each column. For example, we can use 0 to represent sunny, 1 to represent cloudy, and 2 to represent rainy. And do the same with sad and happy. With that, we can go back to the data and replace every value with its corresponding numerical representation. And when we're done with that, we can use this data with any algorithm because we don't have text anymore. This very simple encoding technique of replacing every word with a numeric value is called label encoding. Very popular, of course, but many times it's very problematic. One of the most powerful characteristics of machine learning models is their ability to use signal in the data, even things that aren't immediately obvious to us. This is both amazing and powerful, but we need to be very careful every time we transform the data we have. If we use label encoding, for example, notice how we create a specific order or hierarchy that doesn't exist in the original data. And you can bet your model will notice this and might use that as a signal and make their own predictions. This is a huge downside of label encoding, so most people prefer to use a different approach.
If a categorical feature can take on k possible values, then we will replace it by creating k binary features.
Completely unnecessary, but I found this book online from 1854 written by George Boole, where he talks about using zeros and ones in a clever way to represent a category with multiple values. Today, we call this concept dummy variables, and specifically in machine learning circles, we call it one-hot encoding. The process is also simple. Instead of replacing specific values with numbers like label encoding does, one-hot encoding creates a new column for each value of a category and then fills them out with ones and zeros depending on whether each value is present or not. At the end, it gets rid of all the text. But this time, we didn't add any fake signal to the data by creating an order or hierarchy that doesn't really exist. This makes one-hot encoding one of the favorite encoding techniques that you'll see out there. But of course, nothing comes for free. In the example we're using, we have a maximum of 3 different values in one column. One-hot encoding is perfect for that. But what would happen if we had hundreds, maybe thousands of values? For example, a column storing the zip code of different addresses. If we use one-hot encoding for that, we will end up with thousands of new columns, which will make the data really hard to process. So yes, one-hot encoding is brilliant, but it doesn't work in those cases. And that's where target encoding comes in. The name describes what happens here. This encoding uses the target column to decide how to replace the text in the data. I'm going to start with one value, for example, sunny, and I'm going to ask, what's my mood on average every time the day was sunny? In this case, my mood is happy or 1, 3 out of 4 times the day is sunny, so the average is 0.75. And that's the value that I'm going to use to replace the text sunny. I can then do the same thing for every other value, cloudy and rainy. Average for cloudy is 0.50 and the average for rainy is 0. Notice how this technique is similar to label encoding because it replaces values in place without needing new columns. But it doesn't introduce any weird hierarchy or order like label encoding does. There is, however, one problem. If we aren't careful, target encoding can easily lead to overfitting. Look at rainy here. We have only one data point and we're using it to make a huge assumption. My mood is always sad every time the day is rainy. Can we trust that? This is the Internet Movie Database. Most of us know it as IMDb for short. As of earlier this year, this database contains about 10 million titles and 83 million registered users. IMDb publishes its top 250 ranking of movies based on the ratings of registered voters. But they have to do something clever to maintain the integrity of this list. Avatar 2 is coming out this week and I'm sure it will get thousands of 10-point reviews right away. How can IMDb protect their top 250 list so that a new movie doesn't climb all the way to the top where you have title with many more reviews? This is a very similar problem than the one we have with target encoding, where we need to ensure we don't put too much stock on values that only have a few samples, like rainy. While we don't know exactly what IMDb does today, there are many reports that show that previously they used a formula to balance the ratings based on the number of samples. Here is the formula. We can use this same idea as the final piece for target encoding. Let me show you how that works. There are 2 components here. The first one is the average rating of a movie and the number of reviews. And the second component is the global average rating of all movies and the minimum number of votes required. So for every new movie, the fewer ratings IMDb has, the more they will trust the global average of all movies, which hovers around 7. And as the movie starts accumulating more and more ratings, the less they need to rely on the global average. This is exactly what we need to balance the average we compute when using target encoding. Instead of using the average directly as we did earlier, we can balance them using the global average of the target column, just like IMDb does. And if we do that, a value like rainy, where we only have one data point, will rely more on the global average of all samples. This process is called smoothing, and any implementation of target encoding will do it for you. One final thing to keep in mind. While target encoding is super cool and solves the dimensionality problem with one-hot encoding, it's not a silver bullet. Make sure you try different techniques to see what works best for you.